Thank you very much for the introduction, Professor Monkova. Well, I think thank you all for coming and waking up this early to the first lecture of the day. I must say I'm pretty intimidated stepping on the stage after the show the Bruno and the boys did last night. You know, I'm the first one to act after them, so I'm going to stay here. But I will try just the same to entertain you for the next 40 minutes. Okay, so my name is, as Professor Monkova already said, is Goran Vukelić. I'm coming from the Marine Engineering Department of the Faculty of Maritime Studies, University of Rijeka, which is situated here in Croatia. I'm also currently head of the Materials Mechanics Laboratory, or the Master Lab, as we like to call it. I'm here today to present you a topic on the mechanical failures and material degradation in the marine environment. And actually, this presentation is a joint effort of my team and myself. So let me just, for the introduction, briefly introduce us. We have researchers and engineers coming from several world universities, ranging from North America, Europe, even to Asia. And what we are particularly pleased with is that we have members also from two of the Croatia's biggest national shipyards that are located in Rijeka, and one member from the Maritime Innovation Hub located in Zadar. So a special thanks to my colleagues, to my master students, to my PhD students, and I especially have to emphasize the role of Professor Božić. Okay, sorry, is it better now? Yeah, the role of Professor Božić, who is continuously supporting us in our activities. This is the list of the projects that we are currently working on. We are involved in 3 of the projects that are funded by the Horizon Europe funding program. We have a couple of projects that are funded by our home university, and we have recently ended the project that was funded by the International Association of Maritime Universities and the Nippon Foundation. Actually, that last one was the one that got us into the business of doing research in the maritime field, because this was the time when we started assessing failures of marine machinery. A quick look at the premises, at the facilities that we use for our work. What we believe that distinguishes us from others is the fact that we have a field laboratory that is situated right on the sea, in the small port that our faculty uses. And this is the place where we can perform our experimental research that is focused on the material degradation in the natural marine environment. And also, well, the last picture is the fun picture of the children visiting us, because we regularly host science fair and popularization events trying to attract future engineers and future researchers. Professor Monkova already kindly introduced me, so I think I can skip this part about myself. For those of you that want to know a bit more, we can later chat over a coffee. So where is the connection between our field, the field of mechanics, the field of material engineering, and shipbuilding, maritime industry, and offshore industry? I have selected here several notable failures in the history of the marine industry and offshore industry, starting with the iconic case of the failure of the Titanic's brittle hull when it collided with the iceberg in the North Atlantic. But what really laid the foundation of the failure analysis, the field as we know it today, was the series of fractures of Liberty ships back in the 40s of the last century. In the 80s, we had a collapse of the Alexander Keelat platform on the north of the Europe, and the proof that we are still learning is the fact that the ships are being broken in two even nowadays. I have here put the case of the Mole Comfort 11 years ago, but we have examples that are even more fresh, about 2 or 3 years ago in the Black Sea. And of course, the sad case of the failure of the submersible Titan that we have witnessed last summer. When I started working at the Faculty of Maritime Studies 11 years ago, I was looking for a way to use my background, which is in mechanical engineering and fracture mechanics, and to put it in line with the profile of the institution that I started working on. So besides looking in the history, what happened and how can we collaborate together, I took a look ahead. And here is the list, of course, not exhaustive, not complete, list of the trends in the maritime and offshore industry. We can broadly divide them into the quest of making shipping more greener, so some kind of a green transition, and the digital transition. And I was trying to position myself and my team somewhere in between these trends. So let's just put it practically. I was trying to see where can I find funds for my future projects or for my future research. So what the trends in the maritime and offshore industry at the moment are that we are looking at the alternative propulsion, meaning that we need new fuels that will be used on ships. We are looking to build autonomous vessels. We are looking for a way to build offshore plants that will give us additional renewable green energy, and so on and so on. The use of additive manufacturing and so on. Out of these trends that are currently very pronounced in the sector of in the maritime sector, I have pinpointed several of them, which I will be talking about in today's presentation. So this is actually the presentation outline of the today's talk. I will be talking more about the use of the composites and the biocomposites in shipbuilding and maritime industry, recycling of plastics, adoption of 3D printing or additive manufacturing, building a digital twins, specifically meant to build a corrosion digital twin, and the use of hydrogen and what implications will it have regarding mechanical engineering. Of course, this list is also not exhaustive. It is just, let's say, 5 of the topics that we have selected to work on. Some of them we have made some research, some of them are just in the starting phase. So let's start with the use of the composites and the biocomposites in the maritime industry. Composites today stand as a prevailing choice for small and leisure crafts and some specific Navy vessels. And what we need to understand is that the shipbuilding industry, maritime industry, is highly regulated, meaning that every new built ship has to be approved by some kind of a classification society. And that is the reason that we still don't have large ships that are entirely built out of composites. It is expected that we will have first 100-meter long ship built out of composites somewhere in the 10, 15 or 20 years from now. The Marine Classification Societies, the rules restrict the choice of composites to glass fibers and composite fibers mainly. And where is the problem? The problem is that we still don't know how do they behave when they are in contact with the marine environment, meaning that the mechanical properties of composites are compromised by the absorption of seawater, the influence of polluted processed waters from ship systems, and biofouling. I have here presented the results of the study made by Gabezi and Harrison that was published this year, who tried to see how well do glass fiber and composite fiber composites react when they are exposed to artificial salt water and when they are exposed to elevated temperatures. You can see here that the tensile strength of the glass epoxy composites has a significant drop, a drop that is even more pronounced when we expose these samples to the elevated temperature, not just the salt water, but also to elevated temperature. And that is just the case what we have on ship systems, on the systems for the polluted processed waters. We have a similar behavior of carbon fiber composites, just that this drop of the tensile strength is not so pronounced. For the glass, it's about 20% drop, and for the carbon epoxy is about 10% drop in the tensile strength. This is the study done by Deng and his team that was published last year, and they studied the influence of different aging environments on carbon fiber composites. And what they concluded in their research is that the most severe influence on the mechanical properties, on the strength of the composites, has the combined effect of salt fog and the ultraviolet lighting. And they even performed it's working, okay. They even performed the aging over the 500 up to 2000 hours and see how well do they behave. Just to end this part with the introduction of the things that are already done, I'm going to point to the study that was published in 2017, where the Zhao and his team experimented on different types of composite, meaning that they changed the type of fibers, that they changed the type of resins, but the general conclusion would be that with the exposure time, the mechanical properties are degrading. So where does that leave us? We have to know the fact that at the moment we have to know the fact that at the moment there are about 20,000 units of plastic boats disposed every year in Europe. And that is starting to be a problem. So the engineers, the researchers, the scientists are looking for the way to introduce new type of composites that will not be of such burden to the ecosystem, natural ecosystem. And that is why we have the introduction of the biocomposites. I have here selected a study done by our colleagues from Zagreb, Professor Haramina and her team, where they tested the flax and hemp composites in the natural seawater that they were exposed for 2 weeks. What they concluded is that the flax behaves much better than the hemp composites, but what is severely affected is the modulus of both type of composites. So the questions after just these few studies that I have shown here, the questions that we can ask ourselves is, how does the prolonged exposure to marine environment affect the mechanical properties of composites? And how does the natural marine environment affect the properties of the composites? Why these two questions? Because if you paid attention, you probably noticed that most of these experiments were done in the artificial environment. Some were in the laboratories, and they were done in the accelerated manner. When you expose composites to natural seawater, the effects are a little bit different, and you get a little bit different results. One question also that we need to ask ourselves that I mentioned just before, how to deal with the end-of-life composites products. So this is what we are working on at the moment. This is the study that has been conducted by my PhD student, Goran Vizentin. We have done composite coupons made of the glass fiber composites with 2 types of resins, epoxy and poly, and different stacking orientation. What you see here is the coupons that they were made and were exposed to natural seawater, natural marine environment for 3, 6, and 12 months. When we extracted them, that is the first picture up there, we did some kind of a microscopy, optical microscopy and scanning electron microscopy on them, and we were surprised to see the number of marine microorganisms that have attached to the surface of this type of composites. And we noticed that there is a larger mass of this small micro marine organisms on the polyester resin. That is what we saw just by weighing the mass of the coupons and by looking with the optical microscope. What we see when we dug a little deeper is that these microorganisms have found their way into the structure of the material, making voids in the structure, and that voids can act as crack initiation points. We have tested these coupons to see how well do they retain their tensile strength, and you can generally see that the tensile strength of this type of material is lowered when you expose them over a period of time to the natural sea environment. We use these experimental results to do a regression analysis to predict how well will they behave in the future for the even more prolonged period of exposure. And what we of course know is when the there is a drop in the values of tensile strength. There is also a danger for the remaining fatigue life. So the SN curves also need to be adjusted according to the findings that we have. So the results are published in the Journal of Engineering Failure Analysis. I'm going to list later on the publications, so you can take a look there, or we can discuss it later. But in this presentation, I will not go into the equations, into the methodology, and so on. I just want to open up some questions and see, point out the challenges that we have at the moment, because this is a special niche that is attached to our mechanical engineers. So as I said, on the way we need to deal with the end-of-life composites, the bows that are coming to their end of life after 40 or 50 years of service. And that is what we are facing at the moment. Like I said, about 20,000 units are being disposed around now. And the expectations is that by the end of the decade, we will have about more than 30,000 units disposed every year just in Europe. And plus, there is a plastic waste coming from the blades of the offshore wind farms that is projected to be around 350,000 tons every year just in Europe. So why not recycle? What we know is that we cannot recycle plastics forever, because the mechanical properties of plastics deteriorate, affecting the quality of the recycled product. Here is a study that was done by our Slovenian colleagues some time ago, where they simulated the mechanical recycling of high-density plastics by 100 consecutive extrusion cycles. And afterwards, they tested, among others, hardness and modulus. And you can see for the first 10 cycles that this type of plastics retains its properties very well. After that, there is a drop in the mechanical properties of this type of plastics. This is a very interesting study done published last year by Stapleton and his company, where they tested 3 types of plastics, PET, PP, and PLA, and they immersed them for a month in the water, simulated water, and coupled with the ultraviolet lighting. What they concluded is that the PP plastics are doing the best. They are retaining their mechanical properties the best, while the PET and PLA are having problem in retaining their strength. You can see also here the pictures made by the scanning electron microscopy of the surface of the coupons that were tested. One way of dealing with the problem of deteriorating the quality of the recycled product would be in combining the virgin plastics and recycling plastics. And that is something that is also currently being explored. And here are just a few diagrams showing how well does the recycled PP plastics perform when it is combined with different percentages of combination of virgin plastics and recycled plastics. So what can we ask ourselves if we look at the previous research that I have just shown? Some of the questions that we ask ourselves is how does the prolonged exposure to the natural marine environment combined with the repeated recycling affect the properties of the recycled plastics? How many times can we recycle marine plastics? So the plastic that was exposed to marine environment before it downgrades with their properties, and what are the feasible ways to recycle plastics in the maritime, in the offshore industry? So we have started working, trying to answer maybe part of these questions, part of some questions, and what we started this spring is the testing of the ABS and ASA 3D printed material, which we exposed to the seawater for 1 month, recycled it, made new samples, made new specimens, and then tested them. You can see here some drop in the ultimate tensile strength of such recycled and aged samples, but of course additional testing is currently being done, and we are also seeing we are going to repeat these cycles a few times to see how well do they behave, and also prolong the time of the exposure to the marine environment. I was mentioning how to feasibly recycle the plastics that come from the disposed litter in the marine ecosystems, when we can choose the additive manufacturing technology, because it is today recognized as a new tool in a circular economy scenarios. And it was proven that it is a feasible way, but still a feasible way to deal with recycled plastics, marine plastics. What we need to know is that this type of technology is still waiting to be extensively used in the maritime industry. Why is that the question? Well, there is a lot of objective and subjective reasons. And one of the subjective is that this maritime industry that I think I'm also part of it is highly traditional, conservative, reluctant to change. So they don't respond well to new technologies. Even if, when it is proved, like in the study of Silva and his team, that the challenge of installing printers on board have generally been solved, meaning that you can install successfully a 3D printer on board of a ship, and no matter the waves and the motions and so on, you will get a satisfying result. Why is this important for maritime industry? Because in this way, you can print a spare part for your marine engine right on board, on the middle of the ocean. You can cut down logistics chain supply lines and have your part supplied relatively immediately. But it's still waiting for the full implementation on board of a ship. They have done a study where they implemented on port facilities, and that proved to be successful. This is a study done by Montalvao and his associates, where they compared mechanical properties of 3D printed PLA and the combination of PLA and PHA plastics when they were both exposed to natural seawater and salt spray cycles. So something of a comparison between so-called natural conditions, but I call them so-called because it was done in the laboratory with natural seawater, and the salt spray cycles, which are the accelerated test. You can say, well, no general conclusion can be reached here, because no general conclusion can be reached because there is a mess of the results. Sometimes some of the printed materials show that they deteriorate with time. Sometimes they perform even better. So I guess we need to invest more time and effort in this type of research. So the questions that we need to ask ourselves in this field is, how does the exposure to the marine environment affect the properties of 3D printed materials? Because even if we have the same material, let's say same steel that I will be talking about a little bit later, let's say some kind of stainless steel that was produced classically and that was 3D printed, it will not act the same when it is exposed to the corrosive environment. Now that I'm talking about metals, can the printing of metals be introduced to the maritime industry, and can 3D printed metals be easily joined with the traditional metals? This is the questions that we have asked ourselves, and I started also this spring with one of my students' research. What we did was took stainless steel 316L and made welded specimens, made them in the way that we made the batch that was 2 parts were welded from the classical sheet of metal. 1 batch was made of the combination. Half of the specimen was 3D printed, half of the specimen was a classically made metal, and the third one was only 3D printed. Both parts were 3D printed. We exposed them for a month to seawater, to the natural seawater in the port that I was showing you at the beginning of today's presentation, and we have some initial results. All 3 batches retained their strength well enough, but what we see as a problem is the loss in the strain rate of the specimens that were half or fully 3D printed. So we'll be looking into this more bit this fall when I return on Monday on my university, and we will be surely pursuing this research topic more in the future. Now that we have come to the problem of the corrosion, there is also a strong need to build a digital twin that will be capable of predicting corrosion on marine structures. I have found the info that the global cost of the corrosion is estimated to be 3.5% of the global gross domestic product, and experts are agreeing on the fact that the major improvement in mitigating corrosion will be in introduction of digital twin that has already been introduced in the petrochemical industry, oil industry, gas industry, and we can, what first comes in mind to us is to introduce that kind of a digital twin to predict corrosion and to monitor corrosion on the offshore facilities. I have come across the paper published this year by Vukelić and his team, where he states that most of the failures of the offshore plants happen because of the fracture of the jacket and monopile support structures. We know that the fatigue is a major concern for offshore plants, and that fatigue is furtherly enhanced by the presence of the corrosive environment. So this is something we need to deal with. To accurately quantify the effect of corrosion fatigue on the remaining life of this type of steel structures, we need more experimental work, and we need to determine how the corrosion is affecting the remaining fatigue life of this type of structures, so we can build this type of digital twins capable of monitoring, capable of predicting corrosion on offshore plants. This is the first step in that direction. A model that was done by Neves and his team, published last year, where they did, this was just a numerical digital twin for corrosion prediction on the floating production and storage units of the gas units that are the ships that are converted into the floating stations for producing and storing different types of gases. And their digital twin is based on the finite element method and on the corrosion theory. And coupling these two, they made the digital twin capable of predicting, alerting user when the structural integrity of the ship is compromised. Here are also some questions that we can ask ourselves. First one is that we need to deal with is providing relevant real-time data to build a reliable digital twin. Digital twin will be as reliable as the data that we feed into it. Is accurate. Deeper knowledge of the corrosion pit crack transition stage, because we know that the corrosion pits on the surface act as a crack initiation points that can lead to failures. And based on that, we can make adjusted fatigue SN curves that factor in the effects of the pit size and their morphology. Am I okay with time? Yeah, good, okay. So this is the research that we've done so far in our laboratory. We have made specimens made of welded shipbuilding steel AH36, which is a classical choice for building ship hulls and marine structures. We have exposed these specimens to fresh water, seawater, and now even sea waves to see the combined effect, not just of the corrosive environment, but also mechanical loading from the waves. And once we have extracted these specimens, we did weight loss measurements. We did the tensile strength testing. We expected the corroded surface and accounted for corrosion pit parameters. You can see here, I have just put two pictures. You can find them also in the paper that we have published in the Engineering Failure Analysis Journal. Which show the same images of the specimen that was exposed for 6 months to pure seawater, still seawater, under the 10 meters deep. And the other one that was exposed to sea waves on the surface of the sea. The main difference is that the pits are here, the edges of the pits are rounded because of this combined effect of the corrosion environment and mechanical loading of the waves. Here are some of the diagrams that are also published, and you can check them in the journal papers. We have accounted for the whale loss, try to do some kind of regression analysis, see how well will the steel behave in the future time of exposure, future periods. We have done testing of the ultimate tensile strength and see the drop of the apparent tensile strength of this type of steel, also fitting some curves through the experimentally obtained data to see how well will they behave in the time ahead of us. And we have also numbered the corrosion pits on the control areas, and you can actually see here that the number of the corrosion pits is tending to be lower as the time of the submersion increases, because these pits tend to join together and their number is decreasing. Also, we have measured the corrosion pit depth and also fitted some curves to see how well do they behave in the periods that are ahead of us. So for the last part, I'm gonna, once where we are talking about the steel, the stainless steel, it is the prevalent choice for the storage of hydrogen. And we heard a lot about hydrogen this week. There was a special session. Even today we have one. I'm not an expert in that field, but I'm just going to talk from the position of somebody who is maybe more involved in the maritime industry or knows what will the trends be, hopefully. EU legislation is forcing the maritime industry to lower its greenhouse gases emission. So let's say their carbon footprint. Although it's just 2% of the global production, we need to lower it. These are some of the policies. I see that Professor Monkova is on her feet, so I must speed up a bit. Okay, yeah, and the hydrogen. Okay, just a moment. I need to say. There are still no full solutions to build hydrogen-fueled ships. There are some pilot studies, and in one of the pilot studies we are also involved in to see how well does this type of fuel propel ships of the future. What we need to consider as mechanics, as materials engineer, we need to consider the problem, of course, of hydrogen embrittlement, because still the prevailing choice for storage of the hydrogen on ships would be stainless steel, and the hydrogen is stored at elevated pressures, lower temperatures, which all can contribute to the hydrogen embrittlement. And as I said, I'm no expert in this part, but I can read some of the graphs, some of the diagrams, and they show us that with the lowering the temperature, lowering the nickel content in the stainless steel, the fracture toughness of this type of materials is also decreasing, something that we need to look out when we are constructing ships of the future that will be fueled by the hydrogen. Okay, so I will skip this one and ask some of the questions. What we are all agreed on that the research focus needs to shift to the specific field of storage hydrogen on ships, because we have done a lot thinking about and solving the problem of storing hydrogen on road vehicles, but this is just another dimension. Everything is much, much bigger, and we need to scale these small scale solutions that were intended for road vehicles to the maritime industry. We need to take into account the combined effect of hydrogen embrittlement, thermal cycling, and corrosion, and also the effect of further fuels. We are not stopping with with hydrogen, we are thinking about ammonia, we're thinking about metal, each with their own set of problems. What we are currently working on is the ZEAS project. It's the zero emission Adriatic ship, where in 4 years we should be having our first ship that is fueled by hydrogen that will be sailing across the Adriatic on the national operator Jadrolinija. And our team is in charge of doing the ship feasibility study, meaning the identification of the most suitable type of hydrogen storage tanks in terms of volume, in terms of material, and available hydrogen onboard storage technologies, avoiding possible problems that can come, let's say, like hydrogen embrittlement. So instead of the conclusion, my presentation today, my talk today was not so much oriented at presenting new equations, presenting diagrams, and so on. I just wanted to open some of the topics because it is a specific niche, and to see what are the challenges ahead of us, because the question that I overheard a lot over this last 4 days here on the conference, over the coffee and chatting and so on, is how do you get funded? Where to find funds? The European Union, ship owners, shipbuilding companies are currently investing a lot of money in developing new technology. So the horizon is going to be changed. And I think this is the opportunity also for us to be part of this change, to work on the solutions that will help in avoiding failures that I have pinpointed at the beginning from the century ago and so on. I promised the list of the publications. So here is some of the publications that we have, like Engineering Failure Analysis, International Journal of Fatigue, Ships and Offshore Structures, and so on. If you want to check them, read them, just drop me an email and I will send them to you if you cannot reach them. Just one more minute. What we are looking here on the last picture of my today's presentation is one aged marine structure that is situated in my hometown of Rijeka. If you don't know, Rijeka is the place where the first torpedo was designed and manufactured and tested. And this is the torpedo testing platform that is, of course, not in use for the last 60 years, but it's still standing there as a proof of the engineering that we used to have. Fun fact number 2, our laboratory, our field laboratory is located right beside this platform. So if you think this is a setting that you would like to see for some time, just drop me an email and I will be glad to host you for a week, month, semester, even year or so on, and we can do some research together. Oh, we don't have to do research, we can just enjoy the view. Thank you.